The objective of this screencast is to demonstrate the use of the textbook software for fitting Pxy data. Specifically in this screencast, I will use the Excel spreadsheet. Let's look at the problem statement from the textbook example 11.8. The problem statement tells us that measurements for the 2-propanol plus water system at 30 degrees C have been published, and we're given a reference. Use the pressure and liquid composition to fit the 2-parameter Margulis equation to the bubble pressure, and plot the resultant diagram. So let's say that we've looked up the data. The data are actually given in the problem as you look further down. But let's look at the spreadsheet. I'm going to open the textbook software, and you can find it on my drive in ChemiThermo and then in the Excel folder. We want the Gamma Fit spreadsheet. There are several tabs here. Pxy Fit and Pxy Plot are used for Pxy diagrams. The other three are used for Txy diagrams. Alright, so let's look on the Pxy Fit P, and you can see that instructions are given here. The directions, I won't try to read them here, I will talk you through them. Note that the directions use some cell references, and if you insert additional rows, some of those directions might get jumbled. It's important to recognize that the way that this spreadsheet works is by performing bubble pressure calculations across the composition range and comparing the model and the experimental data. Keep that in mind, and you might want to review the bubble pressure method in order to understand this sheet more completely. The data is plotted automatically, and whenever I update the values, the plot will change. So if I change these values, the plot changes automatically. To work with a system, I first would enter the names in this area, and I would find the Antoine coefficients and enter them in this area. Note that Antoine coefficients are not required because the experimental data may have vapor pressures at the endpoints of the composition. And in this case, the workers did provide those, and I've got experimental vapor pressures from the data set that I've entered here. You'll notice that those agree with the composition at this endpoint and also at the other endpoint. And I just took those and added those here. There is a selector here, flag, that I can choose to turn on and off the whether I'm using the experimental endpoints or I'm using the endpoints from Antoine's equation. Notice that the vapor pressure for 2-propanol does not agree experimentally with that from the Antoine's equation. It could be that these investigators have had some impurity in their sample, and you can see if we look at the plot, if we switch, we can see that the endpoint here is not matched, and if we try to work with an optimization with a pure component vapor pressure that doesn't match the data, we'll get a skewed fit. So it's usually best to use experimental endpoints if the investigators have included them. Alright, so if I go back and let's say I have a new data set and I would enter the liquid composition here and experimental vapor compositions in this field. Notice that if you look in the formula bar, the X2 is calculated automatically as well as Y2. If I don't have vapor compositions, I don't really need them because they're not required for this spreadsheet to work. I also, however, do need experimental bubble pressures, and I would put those in this column. If your data set does not have vapor pressures at the endpoints, you still might want to insert compositions for those points and just leave the experimental vapor pressures empty at the end. You'll still get a nice plot, and by going all the way across the composition range, your plot will also extend across to the axes completely. Alright, let me turn the endpoints back on because I do have them. Notice in this area on the right, I have a description of named ranges, and these variables are used on the different sheets to make the formulas easier to read and understand and debug. For example, if you look at the formula for the activity coefficients, you can see that I've used the parameters A12 and A21, and these are named cells on the spreadsheet. And this is programmed as the two-parameter Margulis equation. It's easy to modify this sheet if you want to work with a different model. You can continue to use the parameter names, and it should work just fine. If you remember how a bubble pressure calculation works, we take the sum of x times gamma times Psat, and that's what I've got programmed in this cell, in this column. The vapor compositions are obtained by x gamma Psat divided by the calculated bubble pressure, and so I'm referencing this column in order to calculate the vapor compositions. The fitting is done by comparing the experimental and calculated bubble pressures, and I do that in this row, in this column. You can see I'm taking the difference, and at each one of these rows I'm going to square the difference, so the difference is always a positive number. Then in the objective cell, I'm going to sum the squares of the differences, which is known as nonlinear least squares. As with other uses of solver, I always want to make some manual adjustments first and get the diagram so it looks kind of close before I go ahead and use the solver. So let's see how it's looking. Okay, it looks a little bit too high here. Maybe if I change one of these a little bit. Okay, that looks pretty good. Now let's just use the solver tool. To use solver, I have to unprotect the sheet. The blue cells can be changed without unprotecting, but to use solver I need to unprotect it. To unprotect, I go to the Review tab and select Unprotect. Solver is found on the Data tab, and since solver has been used on this sheet before, the solver options are saved with the sheet. I'm going to use the objective cell here, and I'm going to minimize that by changing D through E17, which are these two cells. So I click Solve, and solver has converged. Click OK, and let's see how it looks. Pretty good. You can see that I'm using Antoine coefficients here, and so this side of the diagram doesn't look too good. Let me go back. I'm going to change this back to use the experimental vapor pressure at the endpoint. Okay, and now it's missing. You can see how why it's skewed. Let me try to fit this again. Okay, and this is the result that's shown in the textbook example. That's the end of this lesson.